Alright guys, about 10 more seconds. Everybody have their clicker? Still missing a couple of folks. I'll stop at 50. There we go. Alright, excellent work. Yeah, 3. So if I have 9 volts here, when we had some rules, the voltages here, here, and here all have to add up equal to this. And since they all have the same resistance, they all have the same voltage. So 3 plus 3 plus 3 equals 9. Excellent. In the circuit below, what is the voltage across R1? Now with capacitors, the smaller capacitor has a bigger voltage, but with resistors it's the opposite. The smaller resistor has the smaller voltage. So this voltage will be twice this voltage. They both have to add up. A few more seconds, I'll stop at 55, 55. Very good, that's right. 8 volts. I have twice the voltage here as here. And these two have to add up equal to 12. That's 8 plus 4 is equal to 12. You could also say the equivalent resistance here is 6 ohms. So I have a 6 ohm equivalent resistor. So if I imagine a circuit with 6 ohms, 12 volts, that means I have a current here of 2 amps. So I have 2 amps going through this resistor and 2 amps going through here. Anytime I get two quantities, I can find the third. V is equal to IR. 2 amps times 4 ohms, 2 amps times 2 ohms gives me 8.4 volts. We did have a simple circuit series and parallel on the test, but we're going to have more complicated circuits like you had in lab, and even more complicated combination circuits on the next test. All right, in the circuit below, what is the current through R1? A question like this. Start at 55, 55. Question? That's right, good. So looking for R1, each of these have the same voltage. Resistors in parallel have the same voltage, so it's 10 volts across each of these. 10 volts at 5 ohms gives me 2 amps. V over R is I from Ohm's law. Here we have points P and Q are connected to a battery of fixed voltage. As more resistors R are added to the parallel circuit, what happens to the total current in the circuit? So as I add more and more resistors, here, and here, and here, and on in parallel, what happens to this current that's feeding this parallel branch? stop at 55, 55. Let's see, we're sort of all over the board here. So I know one of the rules for resistors in parallel is this, that the total current equals the sum of the individual currents. Alright, where the individual currents are like I1, I2, I3, and then this is the total current. Why don't we try this again? What happens to the total current as I add more and more resistors in parallel? All right, just a few more seconds. I'll stop at 30 seconds. 30 seconds. Very good. This is true for our household circuits. In this chapter, we'll deal with household circuits and how houses are household circuits are laid out. And so a similar thing happens when you add more and more devices in parallel. Your house is laid out in parallel. That total current increases. So we'll see that again later. All right, current flows to a light bulb. If a wire is now connected across the bulb, what happens? Does all of the current continue to flow through the bulb? Half goes through the wire and the other half through the bulb. All the current flows through the wire, or none of the above. A lot of us are wrong here, so let's take a look. What I'm creating here is a parallel circuit that looks like this, where I have the bulb down here and I have the wire up here. Right now, when I have a current that comes in to this branch, it splits up and goes into two different ways. All right, it's going to split up according to the resistance. So more of the current is going to go where the resistance is smaller, right? Y'all have heard that path of least resistance business? That's from electricity. That's where that phrase comes from. Now the wire has a resistance that's effectively zero, basically. All right, compared to the bulb, which has a much higher resistance. So y'all think about that. Change your answer. Most of you had the wrong answer. All right, looking good. Just a few more seconds. I'll stop at 1:35. Like everybody's on board. Good. All right, two bulbs are connected in series to a constant voltage source. When a wire is connected across bulb B, bulb A will do what? That means if I take this wire and I close this switch so that this wire is there, and so bulb B is effectively removed from the circuit. So what happens then to bulb A if I take out B and replace it with a wire? Does it glow brighter, glow just the same, glow dimmer, go out completely, or does it explode? Morning. It's hard to get up with the time change, isn't it? Is it hard to get up? I've been having a hard time too. I didn't get up at like 4:30 this morning. Huh? I know. I didn't get anything done. Alright, I'm going to stop at 1:05. 1:05. Okay, good. It's going to glow brighter than before. By how much will it glow brighter? Let's say that these have the same resistance. Not a factor of 2. What do y'all think? That's good thinking. It's going to glow brighter. All right, what happens to the voltage across that bulb? It goes up. By how much does the voltage go up? Let's imagine this is 12 volts, right? When bulb B is in, I have 6 volts and 6 volts. What happens if I take bulb B out? How much voltage does bulb A have? It's going to have what? 12 volts, right? Now remember our power equation, which describes how bright a bulb is. P is equal to VI. Now our voltage changes by a factor of 2, but our current also changes by a factor of 2. We could think about it in this way, V squared over R. That's a different expression of the power equation. And so here our R remains constant and V goes up by a factor of 2. So our power will increase by a factor of 4. Our voltage increases by a factor of 2. Alright, 2 bulbs are in circuits like below. Which circuit produces more light? That is, which has more power output? Right, just a few more seconds. I'll stop at 45. Very good. A is the right answer. These each have more power, right? What we talked about before, by a factor of 4. 3 light bulbs are in a circuit. Each has a resistance of 1 ohm. By how much is the brightness of bulb B greater or smaller than the brightness of bulb A? We'll stop with this one. We're sort of getting into combination circuits, which we haven't really covered yet. So we might revisit this question in just a little bit. I know each of these branches has 10 volts across it, right? So what's the voltage here? What's the voltage here? Right, these two share 10 volts. So I have 5 volts and 5 volts. I want to know how much is the brightness of bulb B compared to A. Is the brightness of bulb B, first of all, is it brighter or dimmer? Which is it? It's dimmer, right? So is it half as much, quarter as much? It's either C or D, right? Those are the only ones that say it's dimmer. Which is it? D? You say D? No, D. Oh, D. D is the right answer. All right, we'll come back to this. We're going to get into combination circuits, but the answer here is D, quarter as much. All right, so I know that I have 10 volts here, 5 volts here. P is V squared over R. And since the voltage of bulb B is half that of bulb A, that means my power is 1/4 that power of bulb A. All right, we'll come back to these. We have about 10 more, so we're going to do combination circuits today. By the way, I do want to show you, we had the food drive. Y'all did a good job. This is a small class, but y'all did a good job with it. We did get our total. Let's see, what was it in the end? 811. We just made it. Good job, y'all. And let's see, I forget how y'all came out in the end. Yeah, y'all pretty good. I mean, this class has like 80 students in it, so, you know, they're a lot bigger. That was good. Excellent work. So remember what I said as far as the points. That'll be 15 points. Now, there will be an opportunity to pick up another 5 points later. Y'all have to take an assessment later in the semester, towards the end of the semester, gen ed assessment. Y'all did this last year, so in the end, I'm expecting to get up to 20 points. Okay? But I appreciate your work on this. It's not really about the points, right? it's about helping people, because people need help sometimes. Y'all need help sometimes, right? Maybe not with food, but you might need help with other things. So it's about sharing with people and, caring for other folks that are in need. We all need help sometimes. Bonus points are all right too. Yeah. All right, let's look at this circuit. And if you came in late, remember 2 weeks from Friday, no class. So if you want to write that in your calendar, that's, what day was that, y'all? The 27th? Yeah, 27th. That's drop day as well. But if you're going to drop, you should know about now, because we're not really going to have any other major assignments. If you're thinking about dropping the class, please come see me. I don't think anybody here really needs to think about it, but if you are thinking about it, please come see me beforehand. We don't really have any more other major assignments between now and drop day. Is that clear? Don't drop without talking to me, please, because it's probably not nearly as bad as you think. And what's my goal this semester? Not all A's, no. That's not really my goal. No D's or F's. I'd really like to have no D's or S's. It's sort of like a personal goal, but if I give out D's or S's, I mean, that's up to y'all, right? So, all right. No D's or S's, that's what I want. All right. So here, what happens to the total current in this circuit if I add this resistor R? Let me recap our rules, by the way, because it's been a few days. So let me just recap our rules for resistors in series and parallel. For our series, we have these rules. The equivalent, first of all, is R1 plus R2. For resistors in series have the same current. For resistors in series, V equals IR, right? That's true for all resistors. And for resistors in series, the total voltage is equal to the sum of the individual voltages. And then for resistors in parallel, the equivalent is 1 over R1. They have the same, what do they have the same of? No, not the same current. They have the same voltage. That was the same for capacitors. V equals IR. And then we also have something called the junction rule, which is that the total current equals I1 plus I2 plus ... Now, this over here is called the loop rule. And this is called the junction rule. We'll see collectively those are called Kirchhoff's rules when we get into multi-loop circuits. And they're pretty useful for electricians, electrical engineers, when they're dealing with circuits. You want to know. All right. So I want to know what happens to the total current in this circuit when I add a resistor. So I want to ask myself what happens to the equivalent resistor, the equivalent resistance. What happens when I add resistors in parallel to a circuit? What happens, Hunter? It goes down. You can think about your adding paths for the electricity to go, and that means that the overall resistance will go down. So the overall resistance of this branch will go down, and when you add it to this one in series, that means that the overall equivalent resistance will also go down. So then what happens to the total current? Right, so the total current increases. Because the equivalent resistance goes down. All right, let's look at this circuit. I want to know the equivalent resistance and the voltage and the current for each resistor in this circuit. Just try it on your own. First, find the equivalent resistance. You want to start with the smallest portion of the circuit that's either series or parallel, and then go out from there, just like we did for capacitors. You should be able to look at this and just tell me what the equivalent is. It's 3, right. So this 3 and the 6, right here, these are in parallel. 1 over 3 plus 1 over 6. That's equal to 2. Don't forget those fractions that I told you. You'll see those a lot. You'll saw those on the last test too with the capacitors. And then I have a 2 and a 1. So the equivalent then is just 2 plus 1 or 3 ohms. All right. Now I want to know what is the current and what is the voltage on each of these resistors. What is the current through this resistor? It's going to be 4 amps. And I can tell that because if I go down to this circuit, I know that this current, I, is V over R. That's 12 over 3, which is 4 amps. So that means I have 4 amps going through this branch. That's my total current. And that 4 amps travels around here, and it goes straight through this resistor. Now that 4 amps splits here and here. And I want to find out what is that current. What is the voltage, first of all, over R2 and R3? Now I know that resistors in parallel have the same voltage, so whatever's on one is on the other. What is it? 8 volts. So here I have 4 amps. I got these switched up. Let me fix them. This was 1 ohm, and this is 2 ohms for the circuit diagram. So I have 4 amps there. That means that I have V equal IR. I have 4 volts there. And because I have 12 volts here, that means I have 8 volts across this other resistor. Right, so that means I have 8 volts here and 8 volts here. Alrighty? And then you can find the current. Anytime you know two quantities for a circuit, you can find the current. So my I here is V over R. That's 8 volts over 3 ohms. That's 8/3 amps. And then this one is I equals 8 over 6. That's 4/3 amps. Notice, y'all, that here, if I add up these currents, 8 over 3, 8/3, plus 4 over 3, that's equal to 12 over 3, which is 4 amps, which is my total current. That's good because that's according to the junction rule. Those rules for for resistors in parallel, their individual currents have to add up equal to the total current. So I have 4 amps coming into this branch here, and it splits into 2 parts, one of which is twice that of the other, 8/3 amps and then 4/3 amps. Okay? That's really exciting, right? Good for Central Daylight Time, 7:30 class. All right, let's find the equivalent resistance of this circuit. We'll do some that are more and more complicated. Yours will be slightly more about this or slightly more complicated than this on your test. First, find the equivalent resistance. Again, as you get good at this, you might just be able to look at them and tell. That's right, it's 5 ohms. But if you're still working, just go ahead and finish it out. Find out I'm going to give you another minute, and I'll write it out in just a second. Alright, so I start with the smallest part. I add up these 2 resistors. That gives me 3 ohms. I can redraw this. I have a 4 ohm, a 6, a 3, and a 2. And the 6, 3, and the 2, those all add up to give me 1 ohm. That's 1 over 6 plus 1 over 3 plus 1 over 2. That's equal to 1. That was one of those common fractions that I gave you. You'll see those on the exam. And so that gives me a 4 and a 1 ohm, which gives me 5 ohms. All right? Let's say that I have 10 volts here. This is equal to 10 volts. I want to know the voltage and the current on each of these resistors. The voltage and the current. And that's what your test question will look like. It'll be a circuit, combination circuit of this difficulty, or a little bit harder maybe, a little bit more complicated. And I'll ask you, what is the voltage and current on each resistor? Think about that for a minute. You're going to first find this one, right, the voltage and the current on this one, and then these two will follow suit really quickly, and then you'll deal with these two. What is my overall current in this circuit? I have 2 amps. 10 over 5 is 2 amps. That means I have 2 amps here. And so if I have 2 amps going through this resistor and this resistor, what is my voltage here? I have 8 volts here. And then what's left over? 8 plus what is 10? 2 volts. Or I could say IR, 2 times 1, 2 amps times 1 ohm is 2 volts. But I know that 8 plus 2 has to add up equal to 10 because of that loop rule in our rules. Alright, so that means I have 8 volts here. What's my voltage here? In this resistor, R2, I have 2 volts. Likewise, I have 2 volts here. That goes back to our rules. Resistors in parallel have the same voltage. So these 3 branches all have the same voltage. Now, because I only have one resistor here and here, then that resistor is going to have all of that 2 volts. This one's a little bit more complicated. These two are going to share that 2 volts. They're going to split it up between them. If I want to find out what is the voltage on each, these aren't real even numbers, it's going to be some fraction. I can find the equivalent resistance, which I've already found, is 3 ohms. Find the current. If I have 2 volts across 3 ohms, what is the current there? 2/3 of an amp. So I have 2/3 of an amp here and 2/3 of an amp here. So what is my voltage here?
You want to have a 4/3 of a amp?
Now I'm going to have resistors in series have the same current. Right? So whatever current I have here, 2 volts across 3 ohms, I'm also going to have through R3 and R4. So I have 2 volts here. If I have 2 volts, or excuse me, 2 volts, so 2/3 of an ohm, V over R is I. 2/3 of an amp. 2/3 amp is our current. So if I have 2/3 of an amp here, what's my voltage? 2/3. What's my voltage here? Right. 2/3 plus 4/3 is 6/3, which is 2 volts. Let me put that in writing. So here, I know that across this resistor, I have 2 volts, because that's what I had here. And if I have 2 volts, that means I have a current equal to V over R, or 2/3 amps. So I'm going to have 2/3 amp here and 2/3 amp here. Now if I want to know the voltage, V3, that's going to be I, which is 2/3 amp, times R, which is 1 ohm, which is 2/3 of a volt. And similarly, V4 will be I 2/3 times 2 ohms, which is 4/3 volts. Alright, so I have all the answers now would be 8 volts, 4 ohms, 2 amps, 2 volts, 6 ohms. That gives me what? 1/3 of an amp. Down here I have 2 volts, 2 ohms, 1 amp, and then 2/3 amps, 2/3 amps, 2/3, thank you, volt, 4/3 volts. Notice I can look at my currents here, 1, 2/3, and 1/3, and they all have to add up equal to total current, which is 2 amps. So there are lots of little pieces, and they all have to fit together. They all have to coincide with one another. All right, can I do some more examples? Like with the capacitors, this really comes with practice. So lots of practice. Look back at the old test. There are more practice problems there, and also in the homework there are some practice problems. When you get good at it, it comes pretty simple. All right, let's try this series of questions here. Well, where'd my clicker thing go? Did I close it? I guess I closed it by accident, sorry. Is anybody presenting this weekend at LAS? No? Harley, are you presenting? Louisiana Academy of Sciences this weekend is here at Nichols. You know, especially for your chemists, I mean, your engineers are going to move on soon, but for your chemists, if you're not involved with research in the department, there are opportunities for you to work with a number of the faculty. I really recommend that. Or even summer programs in either in the state or in other places. The NSF puts on some nice summer programs. LSU has a nice program. They're really good experiences. They pay pretty well, and you can make $4,000 or $5,000 for the summer. They often pay your travel expenses and your lodging and stuff like that. So it's a good deal for y'all and a good experience. I really recommend that you do that. Or even just working with a faculty member here. They can pay you often. You don't get paid a lot, but you know, campus wages, whatever that is, $8 an hour or whatever. Is that right? Are you working with somebody? Yeah. Who do you work with? Cortez? Yeah. Yeah, what do you get? Research problems? Is that what you get?
Well, like some of the later classes you have to take for research classes.
Mm-hmm.
Kind of stuff like that.
Yeah. Especially if you're going into graduate school, it's a really good thing that graduate programs look at. And I know a lot of you probably are going to go to graduate school. All right. What's the equivalent resistance of this circuit? And if you finish this, there's a whole series of questions. Go ahead and answer those questions. Did I tell you how to finish? What did the hammer say to the drill? Oh man, you're so boring. Been with y'all for too long. You used up all my jokes.
I had a really good one I saw someone.
What was it? Is it vulgar? No? Okay.
No, that's why I thought
Right, yeah. Okay. So a few more seconds, 135. Well, there is the possibility, actually, that, that's right, one of them, I'll show you how. A student approached me to ask about a beard auction for later in the semester, like as a fundraiser for their group. And so they're going to have a beard auction where, I don't know exactly how it's going to work, but the end result is that you lose your beard. But not just lose it, but you lose it in whatever way that they want you to lose it. So like, it could be that I only lose part of it. You know what I mean? Like they could do like lightning-shaped mutton chops or something like that. That's what I'm shooting for. You know what I'm talking about? Like where you shave all this and it's like a biker guy or something. Yeah, seriously. All right. For the circuit in the previous figure, what is the potential across R3? Y'all have it? Let me 12, 6, 4, 3, and 5.4. These are your options. What is the voltage across this resistor? I'm sorry, I'll go through all of these in just a second. I'm going to show you the answers. All right, I'll stop at 55, 55. You're doing really well. If you're not sure, I have a couple people who don't have the right answer. You ask your neighbor. I'll stop at 1 minute. Very good. 6 is the right answer, so I have 6 volts here. I'm going to come back. I'll show you the right answer, how to do this in just a second. I think I had another question. All right, for the circuit, if R3, what happens, if R3 is removed, what happens to the current through R1? Does it decrease, increase, or stay the same? Does it A, decrease, B, increase, or C, stay the same? That is, I'm sorry, I'm trying to show you all the figure. What happens to the current through R1? So, if R3 is removed, what happens to this current? Does it decrease, increase, or stay the same? If R3 is removed, what happens to the current through R1? All right, almost nobody has the right answer. One person has the right answer right now.
Well, you didn't first yet, so.
Oh. I was doing that last one. Only 4 people have the right answer right now.
Who was that one person I got it right?
No, it was on the previous question. Yeah. All right, guys, remember parallel branches are independent of one another, okay? All right, so they all have the same voltage. They're independent. They run parallel. They're independent of one another. All right, very good. All right, just a few more seconds. I'll stop at 55, 58. I'll show you all a picture in just a second. All right. Consider the circuit. Which resistor has the least current traveling through it? R1, R3, R5. Are they all the same? R1, R3, R5. Are they all the same? Which one has the least current? Yeah. Yeah, so just like normal. R1, R3, R5, are they all the same? Which one has the least current? Okay, doing very well. Just a few more seconds. I'll stop at 45. 45. That's right. R3 is right. All right, let's step through each of these. I'll show you all a picture afterwards, and I'll hand back your exam. All right, so here, first I want to find the equivalent. A 2 and 2 in parallel, that's a what? That's a 1 ohm. So then I have a 1 and a 1 in series. That's 2 ohms. And a 1 and a 1 in series. That's 2 ohms. And then these 2 and 2 are in parallel, which we've already done. So that's 1 ohm. Almost everybody got that. That's good. Now, what is the potential across R3? All right, look, this bottom branch, I know, has 12 volts across it. So between this point and this point, I have 12 volts. I know that this is equivalent to 1 ohm. Since this is the same as this resistor, both of these have 6 volts. All right, and since these two are in parallel here and here, these both have 6 volts on them. You'll follow me on that? Yes? And let's see, we already talked about these. You want to see a picture? All right, let's see here. I shaved it off, what, last year at winter time. Those aren't very good pictures, are they? February, March. Oh, there we go. Good picture. Alright. Does that look completely different? How would it be with like Wolverine?
It's not even the same name.
Alright. Okay. I'm gonna hand back your exams now. We'll just. Oh gosh, 10 minutes? Seriously? Yeah, I don't want to get into this business, right? All right, so next time we're gonna get into multi-loop circuits. So that's a whole other topic, but it'll be on your exam. We might finish up this chapter on Monday. We'll see. We're not that far, and then we'll move on to the next chapter, which is I know what it is actually. Let me do something right quick. I'm going to go ahead and pull up the solutions. I haven't put them online yet. I will put them up soon, but it might be later. So I'm just going to go ahead and put them up now so you can go ahead and sort of grade your